Hello and welcome back to the lab. I still am working on the EEPROM portion of the PIC video. It's taking a little bit longer than I'd hoped to get all the reversing done, but it is coming. And in the meantime, I'd like to talk to you about an interesting bug that I recently encountered and how I used ngscopeclient to fix it. So what we're looking at here is the official development board for the STM32MP257. This is ST's second generation application processor platform based on the STM32 peripheral set. And what was attractive to me is that it had essentially the same peripheral set as regular STM32 microcontrollers, which I'm very familiar with, but it also has PCIe, which would allow me to interface it to an FPGA with higher performance and, more importantly, less pins than the parallel memory interface that I use today. And obviously you could just use Linux, which is what ST expects you to do, but I'm a fan of not throwing more software overhead at a problem than I need to, and so I wanted to try and bring it up bare metal. Just my own code running straight out of the boot ROM essentially as the first stage bootloader, putting my entire firmware in that image. I had a serial console, I had all of the cores talking to each other, everything seemed to be okay, and then I tried bringing up the PCIe and I couldn't get it to link up. So obviously the next step was to take a closer look at the signals and see what's going on. I had previously scoped the reference clock, which is over here on the connector, and found nothing of note, so we're not going to spend any more time on that. Just to get you oriented, we've got the sock here. Ethernet isn't actually being hooked up in this firmware, so we can ignore that. We've got JTAG or SWD and trace going out to the orb trace. This probe here is connected to one of the GPIOs. That is our trigger signal that we can toggle from firmware when we see fit to capture an event of interest. Then we've got this ribbon cable is carrying the actual PCIe signals because the dev kit has mini PCIe. I didn't have a mini PCIe peripheral handy to test with, so I've just got a random M2 SSD in this adapter board to break it out to M2. And then over here is a pair of Teledyne LaCroix D420 and D420A. It's just a newer hardware version. 4 gigahertz differential probes looking at the TX and RX. This is a X1 link. It is running at Gen 1 speeds, or at least I'm trying to. It's not training. And capable of running up to Gen 2 speeds, but we're not going to worry about Gen 2 because it's not even getting to that point. So for the sake of this discussion, it's a PCIe Gen 1 X1 link. And then all of these probes are going over to the Teledyne LaCroix WaveRunner 8404M-MS. This is a 4 gigahertz scope that'll do 20 gig samples per second on all channels or 40 on 2 channels. So more than enough for PCIe Gen 1. It is enough to do protocol decoding on Gen 2 and possibly even Gen 3 if you really want to push it. Obviously not with the official firmware, but I've made it do things it shouldn't. However, the one annoyance is that it does not have a CDR trigger. There is actually an option for the scope to do an 8B10B pattern trigger. I do not have that option, so that's why we have the external trigger hooked up. I could do CDR triggering on my other scope on the other bench, the 16 gigahertz SDA. That's about to go back to LaCroix for service, and so I didn't want to hook anything up to it at this point. Okay, so here we are in ngscopeclient. We're going to connect to the scope, and let's just name our channels. This is the receive side, and then we have the transmit side, and then we have the external trigger output from the board. And if we just grab a couple of waveforms and stop to look at them, nothing seems obviously wrong with them. Like, they are not obviously distorted or noisy or anything. We've got clearly defined high and low levels. There's a little bit of looks like ISI or something here, but it's not too bad. And especially on this side, it looks better, which is to be expected because this probe point is closer to the sock. This is the transmit data from the sock and further from the SSD, which is the side we're looking at here. So given that we know the link is flapping, the obvious first thing that comes to mind is signal integrity. So let's go grab some eye patterns of both lanes and see how they look. Let's just make a new workspace to stick our plots in because we're going to be doing a bunch of stuff here. And since we do have some complicated analysis plan, let's go make some groups as well. So we're going to go put the transmit side there. And recover a clock from that. And now add the eye pattern, and we're going to put that in a group on the side of the existing plot. And we're going to name that I pattern TX, just so we don't mix it up with the RX side. And let's get that out of the way. And we're going to make one for the RX side as well. And let's actually just swap these around just to reflect the order that they are in the plots. And that is also 2.5 gig. Again, we are trying to link up at Gen 1 speed and flapping long before we think about training up to Gen 2. So we're not going to be seeing any 5 gig traffic at this point. And we're going to go and dock this up there. And hook that up, and we're going to call that iPattern RX. And let's go make that group a little bit bigger as well, because we're going to be adding a bunch of stuff to there. Okay, so here we've got the eyes from both lanes, and nothing really seems amiss. Obviously, the receive side is a bit over-equalized. It's probably configured for running at much higher speeds. I believe this is a Gen 3 capable SSD, and so it's expecting to be running Gen 3 over a fairly lossy PC motherboard, and we have a fairly short amount of ribbon cable here, and so it makes sense we're going to have less insertion loss. The equalizer is probably going to be way high by default on the transmit side. And then data coming off of the socket, again, we have a wide open eye. This looks like probably close to 400 millivolts of opening, and I don't see any reason to suspect that we have signal integrity issues, but at the same time, the link is flapping, so something weird is going on. So maybe we have some low probability noise or something like that. Let's bring the memory depth up. Let's do, say, 20 million points, and let's start grabbing a bunch. And right away, with only a couple of waveforms, we can see something funny is going on here. We have a wide open eye that looks pretty well defined, and then there's this just low probability, steady back around nothing. It's just something is in there all the time, and it doesn't make a whole lot of sense because of how clean the eye looks otherwise. And if we look at the waveforms here, we can see there is some disturbances going on here that we can see just looking at it. It's not immediately evident whether these are the problem or just PCIe doing its thing. Again, Gen 1 and Gen 2 are AP10B coded. There are going to be some repetitive patterns in the line coded data. So maybe that's what's going on. Let's decode it to find out. So first, we're going to want to threshold it. Since we are working with digital data, everything has to be digital before we can run digital decodes on it. And we're going to AP10B decode that. And then go up to PCIe logical layer. And that is on the receive side. And nothing seems obviously amiss. We've got, looks like these are training sets. So that is indicative of the link flapping. We'll take a closer look at that in a moment. So since we are seeing training sets, we probably also want to decode link training. We'll get that out of the way for a second. And we'll just name that so we can keep track since we are decoding multiple lanes. And then on the other side, let's just go do the exact same thing here. So we threshold, and AP10B, and PCIe logical, and link training. And then let's also, just to make sure we get everything good, let's bump up the comma search window there. And now we can add our protocol analyzers to the bottom of the window, and we're just going to dock it all the way down there. there. And let's also get history. Probably don't need that much. We'll just bump it down to 5 and we'll clear that out next time we trigger. So something weird is definitely happening. So, well, you don't need the thresholded signals, those are getting in the way. So we've got what looks like a valid state with the link of the logical idle configuration across here. And then something happens. Because right around here, we go from being happy and idle and dropping down into link training again. So we're seeing training set 1s, and this is on the receive side. So these are advertising 2.5, 5 gig, and 8 gig line rates. And then on the transmit side, if we go way back to the beginning of the waveform, we are also in a logical idle state. And it looks like we've got some DLLPs there. We can decode that in a minute, see if that maybe gives any hints as to what's going on. And then we get up here and we just go from link idle to garbage. And it happens very suddenly. We go from having essentially no errors to nothing decoding in any sensible way whatsoever. So let's decode the data link layer, see if maybe that gives any hints as to what's going on. And this is RX. And that is TX. So now we can add our protocol analyzers here and for here. And just quickly scrolling through the DLLPs towards the end, let's just clear out some of these other waveforms so we know which ones we're looking at. Let's actually grab another one just because I don't like how it goes bad so early in the waveform. We can't really decode much before things go haywire. Okay, so we're going to only grab the one waveform of history. Okay, so what we have here is the link is in a training state. So we're training on the transmit side, then we start training on the receive side. And the training succeeds. We get back up to logical idles on both sides. So the link is up. Everything is good for a while. Everything is good for a while. And then right here, we start seeing the decode go bad. Again, very suddenly goes from idle to complete gibberish. And then it looks like the link hasn't actually dropped yet because we are still sending a DLLP here. But a little bit later, we do jump back into link training. And I'm guessing, again, this pattern here, this is probably also the transmitter is starting to enter link training again. We probably just can't decode it because it's so corrupted. So the link is definitely flapping. We can see there's multiple attempts at, let's grab some cursors here and get that out of the way. So this is about 2.5 kilohertz frequency, so 400 microseconds. The link is only up for a few hundred microseconds, and then it drops again, and we're just continuously flapping. So this is clearly not good, but at the same time, what we're seeing in the eyes doesn't make a whole lot of sense, because it's not like we're seeing the signal go away and come back. And if we look right around this point where the data goes bad, we're not seeing like big noise bursts. It's not like the lows are in a different spot or the highs are in a different spot. Like the data still looks okay-ish. So maybe it's a timing problem rather than a noise problem. If we're losing sync, obviously that would potentially explain why we're seeing gibberish here, because we might not be sampling in the middle of the eye anymore. So what we can do is go back to our signal here and try to plot the time interval error of the zero crossings in the waveform relative to the recovered clock. And again, that is receive. And we're going to do tie here as well. And I'm just going to make let's get the trigger waveform out of here for a minute. We don't need to be looking at that right now. There are too many signals on the plot. And let's just make the transmit a different color so it's easier to tell what's what. So it is immediately obvious that this is not normal. So we're looking on the same X and Y scales here for both the transmit and the receive jitter. And on the receive side, we have pretty stable, continuous jitter. Again, it's fairly high because we do have a lot of ISI in the signal from all of this overemphasis, but it's consistent and stable. Whereas here on the transmit side, we have everything perfectly fine and dandy, and then suddenly we have this huge burst of jitter. And if we look at the scale here, that's basically plus or minus 200 picoseconds of jitter. Our unit interval is only 400 picoseconds wide. So this is essentially a full plus or minus half a UI of jitter, which is to say the zero crossings in the clock and the data are no longer aligned whatsoever for just this little burst, and then it comes back again. So if we go back to if we put on a dual cursor here, we can just move that so it's not right where we're trying to go. So we have about 400 microseconds between these bursts, and each one is about 30-some microseconds long. And if we look inside each burst, it looks essentially random. It's not like we're seeing a sudden step change in the phase of the clock and then it takes a while for things to recover. The phase basically just goes to complete garbage and is not synced at all, and then recovers. And more interestingly is the fact that this sudden massive increase in jitter happens exactly in time with when our protocol decode goes haywire. And also, if we jump up to the link training, we can see every time we see the link drop back into the training state, shortly before we had one of these noise bursts. And so what's probably happening is the clock is malfunctioning in some way. So we're losing sync with the data, essentially. And then the two devices realize they're not talking anymore. They drop back at the training. By this point, whatever this interference is has gone away, and the training is successful. Very quickly, we return back to L0 and we're happy, start passing data for a little while, and then it flaps again. So now the question is, what's going on? Why is this happening? So another thing that we can try is plotting histograms of the jitter. I don't think it'll tell us anything we're not seeing in the time domain view, but just in case, we'll see what happens. So let's just move some of that around and put up a histogram of the receive jitter and of the transmit side, and then we're just going to make that a new plot and stick that over here. And that's not really telling us anything we didn't already know. We see a clearly bimodal distribution here on the receive side, which makes sense given all the excessive ISI. And then on the transmit side, we see a single pretty Gaussian looking peak, which corresponds to the happy area when we're linked up. And then we see this long tail running pretty much all the way out to the plus or minus 200 picosecond extremes of the UI. So we still have some counts all the way here. And so this is essentially showing us that we have maximum possible jitter under these worst case scenarios. But it's not really telling us anything we didn't already know. And so the other thing we can do is just look at the time domain right where the error burst first starts to happen. we can see, so if we back up a little bit around here, the recovered clock edges, this is a DDR centered recovered clock. And so we see the edges of the recovered clock are pretty much centered in the middle of each of the data bits. So right here, right at the center of the eye, which is exactly where we want to be. And then all of a sudden we jump up here and now we're seeing these transitions are happening, the clock edges are happening pretty much at the edges in the signal, and so we're sampling essentially noise. So it makes sense that we're essentially seeing garbage here, and the recovered clock phase is just jumping all over the place and doesn't seem to show any rhyme or reason as to what's happening. It's like oscillating and phase shifting randomly. And we can see here, it looks like we've actually shifted so far. We're down into the next UI and then back again. And so this ultimately led me to the root cause, which was the transmit PLL on the SERDES losing lock. So what we see here is we're in a happy locked state. Then the SERDES PLL unlocked, our clock frequency starts to become very unstable and we're shifting all over the place. And then after 30 or so microseconds, it locks again. And then the link training is successful, we recover, and then it drops out again. And so the reason for the loss of lock was actually the reference clock to the PLL. I still don't have a root cause for this. The datasheet says that it should work. There is a path to feed the ref clock from the internal PLL. So the setup I had here was 40 megahertz coming in from an external crystal and then getting multiplied up to 2.4 gigahertz by an internal PLL and then divided down to the various 200, 400, 600 megahertz clock domains running the AXI, the AHB, the Cortex M33, pretty much everything except the A35, which has its own PLL, was run off of that. And so one of the divided taps off of that PLL was 25 megahertz, which was one of the reference clock options for the PCIe SERDES. And for some reason, the SERDES PLL really did not like being fed that way. So the solution I came up with was just to set a bit in the SERDES config that pulls a 100 megahertz reference from an external differential input like you would normally use for a SERDES PLL. And that's coming from the same clock generator that supplies PCIe ref clock to the peripheral, and that worked perfectly. And then we probably also want to set up our external trigger to be coming from the GPIO that the board toggles when the link comes up. So now we're going to be triggering when PCIe enumeration starts. And so to see that, we can just rebuild our firmware for the board and reset and run it. And now we've got a wide open eye with no problems. And if we scroll back through some of the protocol decodes here, we can see everything is happy. We have valid TLPs and flow control DLLPs going through. And just to finish things off, now that the link is happy, let's also decode the transaction layer just so we can see what's actually happening during enumeration. And that is the RX side. And the TX side. And now we can add the analyzers for the transaction layer. Here we have on the RX and on the TX. And so scrolling down a little bit to about here, the link is up. And we see a bunch of configuration read TLPs to various addresses in the header region. And then over here, we can see the completions coming in. So this is the vendor ID and product ID, and then a bunch of header fields. And zooming in a bit, we can just check out some of these random. So here we've got, for example, this is just a write of LX deadbeef to test things out. Again, this firmware is not complete. It's not actually doing anything too useful because the link had been flapping so much I wasn't able to bring it up to that stage. But now we've got it working and we see valid well-formed TLPs coming through and the link isn't flapping. The eye is wide open. Problem solved. And just as a reminder, ngscopeclient is open source. All of these protocol decodes, all of this analysis is on GitHub, and you can go play with it whenever you want. Thank you for watching, and I hope this was educational.